I'm going to show you one application of groups, and that's when it's a very interesting application, fairly simple one also. There are large variety of problems on which groups can be applied, but we will restrict our attention to just this one. And we'll use groups in developing this abstraction further from the next lecture. And this application is related to counting. So let's start with an example. Suppose we have a square. Okay. And we want to color the vertices of this square with two colors. Let's say black or white. Fine. How many ways are there to color these vertices with these two colors? But then, if you look at it this closely, and that's where the complication set in, that there are certain symmetries of coloring. For example, if you color this black, this white, 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 and you color this black and this white, 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 then these two colorings are essentially the same, because you can rotate this square and get to the other coloring, or vice versa. So we want to not just color, we also want to know that how many distinct ways are there to color a square in this fashion. And distinctness is counted with respect to these rotations. That if I have a square, I color the vertices, I rotate that square, I get another coloring, that is the same coloring. Now, how many colorings are possible? We just count all black. Okay, that's number of colorings with respect to rotation symmetry. First is all blacks. Another one is all white. Third one is one black, three white. And it doesn't matter which of these four vertices I color as black, because I can rotate it and get any other vertex colored as black and all other three as white. So actually there is just one coloring with respect to rotation symmetries in which we can color a vertex with black and all other three as white. Correspondingly, there is one white and three black. Then, how about two whites and two blacks? How many colorings are there? Two, right? We can color adjacent vertices as black or the diagonal vertices as black. And then all other possible colorings can be extracted by symmetries. Adjacent, two black, two white, diagonal. So we get 6 different colorings, and that's it. There are no other colorings possible. So that is simple enough. But now let me propose a more difficult coloring. Let us say, suppose we have a n-con with say 97 vertices, which is basically similar structure with 97 vertices in it. Now how many colorings are possible? Same two colors, black and white. How do you count? 16? Distinct colorings with respect to this rotational symmetry. We don't want to. So again, all black is clearly one. All white is another. One black is another one. One white is another one. And then rotationally they are all same. How about two blacks? It will be determined by the gap between the two blacks. There will be some number, you can count easily. But then 3 blacks, 4 blacks, 27 blacks. Now if you have to count 27 blacks, you have to worry about how many, what are the gaps between these 27 blacks and with respect to that count. Is that going to be easy? No, that's not going to be easy at all. Now, by the end of this lecture, we'll derive a very convenient way of counting such numbers. And we use groups, as I just said. So how do we use the groups? Well, let's stay with this particular example, although we'll generalize it very soon. We have to factor out, in a sense, the rotational symmetries. Let's try to represent the rotational symmetries in an abstract way. When I say a rotational symmetry, what does it really mean? A rotation is a mapping of, or a rotation of by certain number, right? There are 97 vertices, so how many different rotations will there be? 97 with different rotations, right? You can take this vertex and keep it to itself, that is a trivial rotation, there is no rotation. Or send it to the first one, or second one, or third one. Once you fix mapping of a vertex to the other vertex, all other are automatically fixed. Okay? So there are, therefore, 97 rotations possible. Each rotation can be viewed as a permutation of 1 to 97. Correct? So if I start labeling this vertices by numbers 1 to 97, each rotation I can represent as sending these numbers 1 to 97 to a permutation of these numbers. And that permutation will be determined by where 1 is mapped to. Say 1 is mapped to 4, then 2 would be mapped to 5, 3 would be mapped to 6, 4 would be mapped to 7, and so on. 97 would be mapped to 2, and so on. Right? It's very simple. But this abstraction now allows me to view these rotations as maps. And these are not just maps. Collectively, these rotations form a group. such that pi j of any I is I plus j minus 1, I think. So pi 1 doesn't rotate at all. Pi 2 shifts by 1, or I can name it any which way, but this is, and this, when I say this, of course I mean that when I map 97 and add something to this, I'll reduce it by taking out that folding back. Mod 97, for mod 97, I will need to do this numbering slightly differently. I should have numbered this with 0. Yes, exactly. I should have started with, let's say, the number not 1 but 0, 1, 2, 3, and up to 96. Then, and I would say that instead of 1, I'll call it pi 0, pi 1 up to pi 96. In that case, I can now say that pi j of I is I plus j mod 97. Now it makes sense. I plus j minus 1, no. Now we have pi 0 we start with. So it is I plus j mod 97. Now this means let G be this collection of pi 0, pi 1 to pi 96. This is a finite group under the usual operation, which works for permutations. That's a composition. And it's a simple proof. Pi I composed with pi j equals, pi I means you rotate by I, shift by I essentially, at pi j then shift by j, which is same as pi I plus j mod 97. So there is a closure property, this shows. It has associativity trivially. It is not commutative. Or is it? It is commutative also. In this case, it is commutative as well. Absolutely. Then there is identity, which is pi 0, and there is inverse. What is inverse of pi I? 97 minus I, or 90, is 97 minus I? 96 minus I. 97 minus I plus, not plus I, plus 1.
Pi I and pi 97 minus I.
Yes.
97 minus I plus I.
So you get 0. That's right. So 97 minus pi I is mapped to pi 97 minus. That's sorry. The inverse is pi 97 minus. Agree. Okay. So for these reasons, now we are seeing some interesting structure emerging. Now we can apply our knowledge about groups to understand the number of symmetries, or not just number, we know that there are so many symmetries. Each group element here captures one type of symmetry, and then we can use it to count. It requires a little bit of cleverness, so let me describe that. What is it that this, so we have this group elements. These group elements, each one of them, we apply it to a picture like this, okay, and rotate it. So each group element, that is, we apply to this and we get another such figure. That Am I making sense here? No? Okay. So let me explain a little further. So we have this group of symmetries. Each one of these, I am going to view it as following. I'm going to view each of these elements as operating on a set of elements we call X, which is notationally I write it as pi, which is in G, takes an element of X and produces another element of X. What are these elements? These are the elements which we really want to count. What are the elements we want to count? We have this n gone or 97 gone. We color each vertex. Give some coloring to vertices. How many distinct colorings? We just counted this right in the beginning. Set X is the collection of all possible colorings of 97 vertices. That is 2 to the 97. Each vertex can be either black or white. There are 97 vertices, so that is 2 to the 97. So that is my set X. When I apply a pi in G on one element of this, that just rotates it and produces another element of set X. This is an important point, or rather important view. It's not very difficult to understand, but it's an important view to keep in mind. That these symmetries, which are pi, the rotations, I will view as taking one coloring of these 97 vertices and sending it to another coloring of these 97 vertices. Okay? Any questions on this? No? Now, what is it that I want to count? I can put it across in a very nice way. Let's say here are all the circles. These are all elements of the set X. Each of the point here represents one coloring of the 97 vertices. Okay? Now each coloring, if you look at it and apply a pi on it, it would be mapped to another coloring. Let's say this is mapped by pi 1 to this, maybe by pi 2 to this, and so on. Keep in mind that there are some pi's which will map this point to itself. For example, pi naught will map an element to itself. It doesn't change the element. But that's not the only pi that may map an element to itself. For example, if you look, say this element is all black. and you apply pi on it, where does it go to? It stays here. No matter which pi you apply, you just stay here, right? So all pi's will just keep it to itself. So this will look different. So for different elements here, we'll get different structure. That some pi's will take it to some other nodes, some pi's will map it to itself. Okay. Now let me define. So we create this picture. Keep this picture in mind. This is what we have these elements, and then we create these arrows corresponding to the different pi's taking that element or node to another node. And now let's define a relation. There exists a pi in G such that pi A equals B. This is for AB in X. So when two nodes A and B in X are related, what does it say about A and B? It says that there is a rotation of A that gives me B. Fine? And therefore A and B are, from this rotational symmetry perspective, are the same. So we don't want to count, in our original counting, we don't want to count A and B separately. We want to count them together as just one element. So this relation is what we want to enforce on this set, and then count how many distinct unrelated elements are there. So exactly, that is what I am driving at, but for that we have to first show that R is an equivalence relation. And that's easy. Well, firstly, A is related to A, pi 0, A is A. Second, A related to B implies B related to A, since pi A equals B implies pi inverse B equals A. We know that pi 0 belongs to the group G. It's an identity map. We know that if pi is in the group G, then pi inverse is also in the group G by the group property. And 3, A related to B and B related to C implies A related to C, since pi 1 A equals B and pi 2 A. I don't want to use index 1 and 2 here because I used it slightly differently. Pi A equals B and pi prime B equals C implies pi prime composed with pi A equals C. And pi prime composed pi is again by the closure property of the group belongs to the group. So there is another element that's it. So here is another demonstration that there is a close relationship between equivalence relation and groups. So this group G induces an equivalence relation on these elements. So now the picture looks much nicer because now we have that there are equivalence classes here with respect to this relation. By the way, this is an equivalence class of its own. This all blacks, because every element in G takes it to itself. So this is a solitary equivalence class. And now the problem is the number of equivalence classes. Each equivalence class gives me one distinct element, because the elements of an equivalence class can be transformed to each other via these rotations. So we just need to count how many distinct equivalence classes are there. That will give me exactly the number of different colorings. Okay? Are you with me so far? There is a slight problem because equivalence classes, different equivalence classes will have different number of elements. We saw example. Here is an equivalence class that has just one element in it, whereas some other equivalence classes will have many more. So we have to do a slightly careful counting. We cannot count it very easily. So how do we count? Well, here is a trick we use. So in general, we are given a finite group G and a set X such that pi is a mapping from X to X for pi in G. Then G induces, we just saw an equivalence relation on X, and we want to count the number of equivalence classes. So now I am removing this connection with this rotation group. I am saying take any finite group, and in fact this group need not even be commutative, could be any group. We are given a finite group and a collection of elements X, such that every element of finite group maps elements of X to X. This induces an equivalence relation on X, and then we want to count the number of equivalence classes. How do we do that? For that, define a set Y as Y is a set of pairs. One component of a pair is pi in G, and second component of the pair is A in X. And pi A pair belongs to the set Y if pi of A is A. That means this element pi of the group G does not disturb A, it sends A to itself. Pi need not be identity. Pi could be mapping some other element to a third element. That is possible. But it just so happens that it keeps the element A to itself. What is the size of Y? Well, I'll write it in two ways. Size of Y, first way I'll write it as, it is sum over pi in G X pi, where X pi is set of elements A in X, so that pi A sends A to itself. This is trivial to observe. So I am not doing something special here. I'm just saying that see, pi contains the pairs pi, y contains the pair pi and a for all pi and all a satisfying this equation. So just split that and write it as sum over all pi's in G and x pi, where x pi is all the elements a and x, such that pi is a. So this set y, I am dividing it into subsets, one corresponding to each pi, and then summing over, size of x, not just x. Okay. The other way I'll write y, size of y as sum over a in x, we can guess, GA. So that's the other split. You fix one for each a in x, you just count, again this is a size, count the number of pi's that map a to itself. So that's a slightly different split of y. Now I am splitting y in subsets, one for each a in x, and then counting how many pi's map that a to itself. And clearly both of those summations give me the same number, which is size of y. Therefore, we can write equality between these two sums. Pretty straightforward so far, but the cleverness here is already used, which is to define this set y and count it in two different ways. Once we set this equation up, the rest is pretty straightforward. Keep in mind the final target. What is the final target? I want to count the number of equivalence classes. Let's focus on this sum. This sum I'm going to write slightly differently, and for that let's go back to the picture. Keep this sum in mind. What is this sum? This is sum of for every element a of x, the number of mappings or number of pi's of G that keep a to itself. If you go back to this picture, what we are talking about is how many, here is an element a, how many of G's map, how many of pi's map this element to itself. So that is how many arrows are in this picture going from this element to itself. That is GA. If this element is A, GA is in this picture the number of arrows that send A to itself. Correct? Feel free to stop me and ask a question or clarification. Now I'll just make one final observation and then we are done. If A is related to B, then size of GA is same as size of GB. That means if I draw a sub picture of that picture, say this is A and this is B, A is related to B. So that means there is a pi that maps A to B. And now I want to see, my target is to see how many self loops are there in this picture, which are arrows which send A to itself. Similarly, I want to count how many self loops are there on B, and I want to relate these two numbers. And the relationship is that the numbers are the same. Why? Well, okay, let's prove this. Suppose pi A equals B. Then for any sigma in GA, take a map which sends A to itself, and I'm going to transform this map into a map that maps B to itself. How do I transform it? Composition with pi. That wouldn't be sufficient. I want to go pi sigma pi inverse is in GB. Why? Just this is another map in the set, the group G. What happens when you apply this map on B? Apply on B, pi inverse will take B to A, then sigma will take A to itself, and then pi will take A to B. Okay? Since pi sigma pi inverse of B is pi sigma of A, which is pi of A, which is B. So we have established a mapping from GA to GB. Therefore, we have a map from GA to GB. And that map, let's give it a name. Let's call it psi. Yes. Colors, the relative positions of colors are the same, you're right. The same thing, you are very right. That's intuition. And I'm just putting that intuition in formal symbols, that's all. Otherwise, there is nothing very special happening here. You can see, I think, instead of giving further details, I think it's easy to see that psi is a one-to-one and onto map. Therefore, size of GA is same as size of GB. Psi maps GA to GB. It's a one-to-one onto map. Both are finite sets, so their sizes are the same. And once we have the same sizes, I'm done. Just let's go back to this. Let's rewrite this as splitting this further into equivalence classes. Say O is an equivalence class. Summation A is in O, size of GA. So I'm writing this sum and splitting it. First sum going over all equivalence classes, and then next sum going over all elements within that equivalence class. So this, in the inner sum, size of GA is the same for every element. So this is, I can write as size of O times size of GA. Now what is size of O times size of GA? Go back to this picture. Here is an equivalence class. Size of GA is all pi's that map A to itself. That's the number of pi's. How many elements are there in all in the equivalence class? That number we don't know, but what we know is that if you take any pi in G, it will keep either A to itself or send A to some other element in the equivalence class. Okay, and so there are size of G different elements in G. Each one of those elements corresponds to one arrow in this equivalence class. And size of GA times size of O, this is the equivalence class O, is exactly equal to number of arrows in this equivalence class. Why is that? This I am going to saying is O is an equivalence class size of G. To prove this, I will just appeal to you to think about the last lecture or the lecture before and observe the following. G is a group. First observation is that GA is a subgroup of G. Okay, and then when we quotient G with GA, you get equivalence classes. Each of these equivalence class corresponds to one element here. That is, this is a GA. GA is here as a subgroup. Then there is other group. So if you look at G and quotient it with GA, you will get exactly the number of distinct elements in an equivalence class. And I'll leave you to prove this. It is not difficult, just need to observe that. And now I have number of equivalence classes. Just look at this. This sum is running over all equivalence classes. And inside the sum, we all have the same number, which is size of G. So number of equivalence classes is precisely 1 over size of G times this sum. What we just proved is called Burnside's theorem. That number of equivalence classes equals 1 over size of G times sum over pi in G x pi. This theorem is applicable in general for all groups and all x's where G operates on those x's. These are finite groups, of course. And it's a very useful tool in counting. Why? Let's get back to our original example of 97 vertices. How many pi's are there? 97? In the group G, there are 97 pi's. Let's count x pi for each one of them. What is x pi 0? Size of this. Pi 0 maps an element to it, each node to itself. There are 97 nodes in that figure. Each pi maps each node to itself. So how many distinct colorings are there? How many colorings are there which are preserved by pi 0? All? What is all? What is that number? Or 97. Okay. How about x pi 1? X pi 1 sends one vertex to the next one. And next and next and next. How many colorings would be preserved by pi? if the first vertex number 0 has, say, color black, pi 1 will map 0 to 1. In order for that colors to be preserved, 1 also must have color black. 1 goes to 2, so 2 also must have the color black. 2 goes to 3. So all of them must have the color black or all white. So that's just 2. How about x pi 2? Here 0 goes to 2. 1 goes to 3. So 0 and 2 must have same color. 1 and 3 must have same color. So 0, 2, 2 goes to 4, 0, 2, 4, 6, 8. These even numbers must have the same color. 1, 3, 5, 7, 9, odd numbers must have the same color. Counted modulo 97. So the next observation is that actually 1, when you start moving from 0, 0, 2, 4, 8, when you come to 98, that is just 1. Sorry? And then? No, so it would, I'm claiming that it is all white or all black only. Because 0, suppose 0 is black, then 2 must be black, 4 must be black, 6 must be black, and so on. 94 must be black, 96 must be black, 98 must be black, 98 is 1. 1 is black, then 3 must be black, then 5 must be black, 7 must be black. So all we've gone through. Sorry? So modulo 97, the question is, yeah, how many can you cover all the elements? So this is also 2. And in fact, all of them are 2. And this falls out of the fact that since 97 is a prime number. In case 97 was not prime, suppose we had it 9, then this would be different, because 0, 3, 6, 9. 0, so that would be 1. Oh, that's what you were saying? Okay, perfect. So that's, I didn't understand that. And that's it. We have now our count. So the number of equivalence classes is 1 by size of G, which is 97. And this sum inside is how much? 2 power 97 plus 2 times 96. That is 192. So therefore we have an exact count of the number of equivalence classes. Yes. Number of elements, sorry, number of elements in G. If the G has a large number of elements, then you have a more difficulty in counting. Then you would have to do a little more involved counting, but that still would not be, it will depend on number of factorizations of what that number is. The key gain here is that this count is now 1 for each element of G. G will typically, which is a set of symmetries, will have a small number of elements. So you can do this counting much more easily compared to earlier where we were looking at all possible ways, and that is really too many. So we are done with the groups, and I will mail you the assignment also, the second one on groups today, and send you a submission deadline.